Hello and welcome to the Chemistry Made Simple podcast. I'm your host, Matthew Macario, and this is the podcast where you get chemistry confident and we take you from point A to grade A. Hello and welcome to the podcast, or welcome back if you've been here before. Great to have you here again. I hope that you're well and studies are going well too. Today we're going to be continuing our mini-series about kinetics, and we're going to be following on from collision theory. And today we're talking about the Maxwell-Boltzmann distribution. So we're going to define what that distribution is and how it's shown on a graph. We're going to talk again about activation energy, and we're going to talk about how you use that distribution, how you compare that distribution at different temperatures. So the Maxwell-Boltzmann distribution is a way of showing the energy profile of a population of molecules or a substance. And we do so on a 2D graph. So on the x-axis across the bottom, we have energy. And on the vertical axis, on the y-axis, we show the proportion of the molecules present that have that energy. And the distribution shows the profile of energy distribution at a given temperature. So some things to note is that we usually have the origin at zero energy, and we should always show that there are no particles with zero energy. That's just not possible at any temperature above absolute zero. The curve of the graph rises until we get to the most probable energy and then dips quite sharply towards the right as energy increases. So the peak is showing the most likely energy, the most common energy of particles within that population of molecules. It's not the average energy. The average energy is usually further to the right. It's a higher energy. So something worth noting there is that most particles within the population of molecules will have less than the average energy. So it's also possible for us to mark the activation energy on the x-axis if we happen to know what reaction is possible to take place here. If we extrapolate across to the y-axis, we can work out what proportion of molecules have that activation energy, have enough energy if they were to collide with the other reactant, that a reaction could occur. Okay, so let's revisit activation energy. Activation energy, as we said last week, is the minimum amount of energy required by the reactant molecules when they collide for a reaction to occur. If the molecules don't have that much energy, then the reaction cannot proceed, no matter what the orientation of the molecules. Okay, and the final thing, but probably the most important thing about the Maxwell-Boltzmann distribution curve is what happens to it if we alter the temperature. And we usually talk about increasing the temperature. What happens if we now take the same population of molecules and increase temperature? So what will happen is the area under the curve stays the same because that represents the number of molecules present. The steepness of the curve towards the most common energy is shallower, and that peak is lower. After that peak, after we've achieved that peak of the most popular energy, the steepness of that curve back towards the x-axis is much shallower, and in fact, at any particular energy along there, the number of particles, the proportion of particles with that energy is considerably higher than it was at the lower temperature, the first distribution that we might be comparing with. And it's really important to understand that because it's a very common exam question that you'll be asked to compare the Maxwell-Boltzmann distribution at two different temperatures, or to describe what change would happen if you change the temperature. Okay, so we've talked about increasing the temperature, and what we would find is we haven't changed the activation energy. That is the same for the reaction, but the number of particles, the proportion of particles that have that activation energy will be higher at that higher temperature. And therefore, that's an indication that there's more molecules at a higher temperature that can react, and therefore there is more likely to be reaction at that higher temperature. Okay, so we've talked about what happens if we increase the temperature. Actually, the exact opposite happens if we were to lower the temperature. That initial curve would get steeper. The number of particles with the most common energy would be a higher proportion, and the actual energy would be further to the left, it would be lower. and the number of particles, the proportion of particles that have the activation energy would be lower too. So that's really important if you need to describe or sketch a Maxwell-Boltzmann distribution at different temperatures, if you need to say what happens to the curve at a higher or a lower temperature than the starting temperature. Okay, so what we talked about today, we've talked about the Maxwell-Boltzmann distribution being effectively a graph with energy on the x-axis and proportion of particles with that energy on the y-axis. It's an energy profile for a population of particles. We've talked about marking the activation energy on the graph, if we happen to know that. We've talked about what happens to that profile, to that curve, if we increase or decrease the temperature. And we've also said that's something that comes up time and again in your exam questions. So do learn how to sketch or describe what happens when you change the temperature, what happens to that curve. Okay, so if you still have questions on this topic, then I'd be delighted to help you. Please do come over to the podcast Patreon community at patreon.com/chemistry made simple. I'll put a link to that in the show notes. You can also find me on Instagram at chemistry made simple. If you want to support the podcast in a different way other than Patreon, then please do rate and review on your podcast player, or I've set up a Buy Me a Coffee and the link is in the show notes too. Thank you for listening to this episode. I hope you found it useful, and if you have had value from it, do consider visiting our Patreon community at patreon.com/chemistry made simple, where you'll be able to ask deeper questions about this topic and get more support for your studies too. So I look forward to speaking to you again in the next episode, and until then, do look after yourself and goodbye.